So I hope you can hear me clearly. Sorry for the long title. We tried to come up with the most useful one so that everyone roughly knows what we are doing. DOBB-BVH is the acronym that we are using, and this is a combined collective work with all the colleagues at AMD and also Matthäus, who then moved to Intel. And we are trying to explain also, as you can see in the image, how we achieved the performance speedup. So there's still plenty to do with BVHs and explore those, and I will briefly explain the concept and the results. Oh, sorry. So in real-time ray tracing, you basically have a scene geometry where usually it consists of triangles, and you want to simulate light transport. Usually your scene geometry consists of triangles, and what you want to find out when the light bounces or wherever you want to explore whether there's any hit or any occlusion with the light source, you want to simulate that. And you want to quickly identify the closest or any hit. However, testing millions of primitives, or triangles in that case, is very expensive and prohibitive. So you want to be fast in identifying those. So what you usually do is you build an acceleration structure around it. And the state of the art in the industry, as you can see also in the video, is that you use a bounding volume hierarchy. So you enclose your geometry with, let's say, a bounding box, which is axis aligned and has min and max values stored. And with that, you can early reject the rays which do not hit with any of with larger parts of the geometry and just focus on the hits that are potential hit candidates where you actually intersect with. And ABB is basically the term for axis-aligned bounding box in that sense. And usually you refine your splits until you enclose just a number of primitives, let's say 2 or 3 or 4, and then you can focus whenever you encounter a leaf node, you can then intersect against those primitives to get the actual hits. And modern GPU hardware actually supports Ray-BB or Ray-primitive intersection, so that accelerates traversal a lot. And the goal with BVH building is basically to minimize the surface area. I wrote down the formula here. What it boils down is that you want to minimize the surface area of your child nodes in your interior node, for instance, compared to the surface area of your parent node. Now, there are alternative bounding volumes, not only axis-aligned ones. It just depends on how complex you want the representation to be. So for spheres, you just need a center or radius, but then you lose culling efficiency. What you actually want to do is minimize the surface area and align the box so that it fits the underlying geometry nicely. And one thing that people came up with very early, decades ago, is to just apply a transform to the axis-aligned bounding box. So you just need a min-max value, and you apply the rotation so that your box is nicely aligned with the orientation of your geometry, which is called OBB. You could also use a discrete-oriented polytype, where you have k-bounding planes to also increase the culling efficiency. However, in the last 2 years, we've seen attention to OBBs because it seems compelling. You just need one additional information, like a rotation, and then you could already decrease the surface area and also increase the culling efficiency. A quick outlook to what we are getting at is with our approach. You can see on the right image here that you have the bright spots, which are the iterations. So boils down to the number of internal node visits or leaf node visits aggregated, and you see the expensive regions there, and what we wanted to get at is reduce those expensive regions and bring down the number of iterations that you need to take per array, and also increase the traversal, and we wanted to find out if that's possible. Prior research based on that, and there is a lot of work in terms of looking at hair and fur or long thin primitives. One interesting idea that catched our eye was the work by Reyes et al., where we have a parallel transformation of BVHs into OBB trees. And the nice trick, what they actually did is they took an existing ABB-BVH and transformed it directly to an OBB-BVH by using the existing topology. Just that you've heard the term here, they used the detour algorithm. So what they did is they have the extremal points at each subtree, and they compute the extremal points there. Plus, they construct a base triangle and connect those so that you have 2 tetrahedra. And with those, then you iterate through all the edges of the tetrahedra and find out the OBB that minimizes the surface area. Martin Kaczmarek and Bittner also did a lot of investigations in OBBs. And one that also is similar to what we do is that they transformed an ABB or DOBB-BVH to OBB-BVHs and also showed how that improves traversal. And they also demonstrated that you can build this BVH in milliseconds. The current state of the pi resort is basically what we are actually taking for our work is the GPU-based ABB to OBB conversion. What they have is an unlimited or a guided OBB representation, but it can be arbitrary depending on how you guide those. They also use the detour algorithm or an intermediate representation. We also explored with the detour algorithm, but we found it a bit costly to do that at each step. So I quickly mention what we do instead in a few seconds. In terms of memory requirements, so if you have a wide node here with 4 children, what you need to do is you need to store a separate rotation per child. That means if you use the full 3x3 matrix, you need to have 9 float values that you need to store for each of the children, which is very much, or there's some way of indexing, but you need more data that you need to store in an interior node, which in worst case requires multiple cache line fetches, which also could slow down performance. And in terms of traversal, they have a pure software implementation, which they show a SIMD kernel, and they do Ray-OBB intersection per child. Now, what we're actually trying to focus on is that we now propose in our work a fixed set of discrete rotations. I will quickly explain what we're doing there, and use simpler heuristics to construct the OBB on the GPU. And one change that we did is that we have one single OBB rotation for all the child nodes. And this is the underlying assumption that if, like at the leaf nodes close to a meshlet, everything is commonly oriented, so there is a better chance that you find a common orientation, so maybe one rotation suffices to reduce the surface area. Memory requirements in that sense in our work is that we have low resolution projection proxies, which we use to then construct the OBBs, and we just use a few bits for the OBB encoding. And the difference in our SIMD traversal is that we have hardware accelerated Ray-OBB intersection. So in terms of the discrete set of rotations, so that's the base of our builder. What you can imagine is you have this simple representation is you have an axis and you have an angle that you rotate about, and that already defines your one rotation where you can align all your bounding boxes. What we propose in our work is that you set or pick a number of angles that you want to choose from, and then you have a fixed discrete step size around the circle, and with that you get already a selection of candidate rotations. Plus, we discretize the sphere, so you can use any low proxy representation of a sphere and take, for instance, the vertices and get the axis. And with that, we construct different sets of rotation frames that we allow our builder to pick from and use that. The encoding is pretty trivial in that sense that you just need the number of bits, because we just need one rotation to represent. So you just need to use as many bits to index into all the discrete rotations. And along with the additional data that you need to add an internal node, you just need the min-max values in the rotated space and an OBB index. And with that index, you already know which rotation you're actually take from, and you can also use it in traversal then. Our traversal just modifies in that sense that what you need to do is you fetch the transform based on the index, then you get a local ray which is transformed in the rotated space, and then you use your method to intersect the children against the rotated ray, and you get your potential hit candidates. So the overview of our GPU-based builder is that we start with a BVH2 build, and to create the axis line bounding box in the initial topology, so we convert the geometry to the internal scratch node format needed during our build. We perform Morton encoding, and then there was a nice paper from Karsten about named H-block, which we used to create the BVH2 topology. Then we do a collapse step where we open the child node with the largest surface area and create the target width, the target branching factor. Then we do the hardware format encoding, where this allows us to do the hardware accelerated Ray-OBB intersection, and we have the final DOBB phase. So our approach is basically just hooked up at the end and tries to convert the existing topology to OBBs if it's applicable, and it's a bottom-up approach. So how does this phase work? It consists of 4 steps. So the first step is the leaf node. It happens at leaf nodes where you can do everything in parallel and compute it in isolation. It's the OBB mapping and initial proxy computation. Then you select an OBB candidate. Then you do a refitting and decide whether you finally want to construct those. And the proxy computation is needed because when you go up the tree, you need some representation to refit your bounding boxes. So I'm starting with the first step here at leaf nodes. How does the OBB mapping basically work? So in our leaf nodes enclose either one triangle or two triangles, in that case a triangle or a quad, and we take like either the shared or non-shared edges and the normal and have a basis, initial basis that our triangle set is following. We map this to polar coordinates and have a lookup table where we can just decide which of the rotations is best for this combination. And for the proxy computation, the problem is we can't represent all the KDOB axes that could potentially be built up from all the sets because there could be 200, 400, depending on the set. So what we decided to do is we use a 26 stop. That means we have 26 float values. That's 104 bytes that we need to store per node. And that allows us to stay within a cache line and represents at least parts of the KDOB axes that are used by the rotations. And we can use that as a proxy to refit. The projection is pretty straightforward because you use dot products to project your geometry onto the axis. And then you end up with a final representation where you have all the projection values that you need later on in the pipeline. The candidate selection is, in our case, pretty easy because we tried different kind of variations. So for this wide node, either having children as leaf nodes or interior nodes, you have the OBB candidates that were propagated up. And we try to brute force it or try to stochastically sample it. The problem is that also takes some time. And the cheapest and effective option in our case is that we just compute the surface area of those children and just take the one that has the largest surface area, because that is the one that is most likely to be hit, and take that. Now, once we have the candidate, we do the refit step. So what we do is we take the proxies and we treat those as apex point maps. I refer to the paper if someone is interested in explaining it. I have some slides. But what it does, basically, the intention is that if your rotation axis is not aligned with the KDOB, we are able to create a conservative bounding box based on that, and then create the final OBB bounds based on the rotation that we picked. And then we use the cost function. In our case, we just aggregate the surface area because we're trying to minimize the SAH. We compute the surface area of the ABB bounds and then the surface area of the rotated bounds, and introduce an user-defined threshold, so that allows us to control how conservative we want to be with the construction. And if the cost of the rotated version with the OBB is smaller than the equivalent of the ABB, we then construct an OBB node. The last thing is the proxy computation for interior nodes, and what we basically do is first we propagate up the best candidate that we picked from the prior step, and then we take the KDOB projections that we already computed, do some min-max operations on those axes, and then we get the new representation for the new node, and then propagate it up. And this is repeated in a bottom-up way until we use just a stopping criteria or a root node is reached. Now for the analysis. What we now wanted to, based on the builder that we provided, wanted to measure the actual performance and do some analysis in terms of the traversal behavior and statistics. We measured this on the latest RDNA4 graphics card from AMD, which allows hardware-accelerated Ray-OBB intersection. And we used 5 datasets with varying complexity and important static scenes in this work. And you can see on the images there's a tree which has arbitrary oriented leaves. And that's something that we wanted to figure out if our approach is actually working for that, because you can't easily find a consistent orientation. As well as the dragon, for instance, has very tiny, small triangles. Some of them are non-axis aligned and rotated, and maybe OBBs benefit here. But we're trying to analyze those data. For Bistro exterior in the middle, it has a mixture of rotations due to the foliage and the scene geometry, and some parts are axis aligned. And the hairball is resembling the hair and fur geometry, which previous authors have also analyzed. The same for power plant. Some acronyms that we use during the analysis, just to show you briefly, because it's sometimes hard with all the terms, but what we focus on, what I explained to you, is the GPU version, the algorithm that we mainly focused on. But we also wanted to find the upper bound, at least with our shared rotation, what's possible. So we also implemented a CPU version of that, where you have unlimited resources. So you have all the information of all the possible axes and the projections with those, and we just brute force through all the possible rotations and see what's the maximum that you can achieve. And you did the same if we just placed that and used the rotations here per child. And in our case, we used over 100 discrete rotations, so we can fit those into 7 bits, and then converted those from a BVH8. First, the BVH quality focuses on surface area. So as I said, we wanted to bring the surface area down, so any reduction that you can achieve is desirable. And as already anticipated, Vike and Dragon are the ones where we saw not many benefits, especially with our approach. So the per-child construction is quite effective for most of those, but you can see with a shared rotation, it degrades, although the CPU version is still competitive with the per-child construction of OBBs. However, the GPU version suffers a bit due to the simple heuristics that we choose. But at least for the good scenes like the hairball, bistro exterior, for those we can reduce the surface area by nearly 50%. And for the GPU version, we achieve at least 25%. So there's definitely a potential that SEH maps to, so some authors showed that SEH maps to ray tracing performance, and we anticipate an increase in performance here as well. Another thing that we looked at is for SIMD traversal, all the lanes, for instance, execute ray traversal, and some of them have to wait if they are long-running rays and you take a lot of visits for certain rays to complete, or you block anti-waves if some of the waves are busy. So you can see here, I'm showing an image here. So you want to bring down the bright yellow regions to, let's say, from the yellow to the blue. That means you want to bring the iteration counts down. And that is quite important because then you basically eliminate the costly regions and try to accelerate the entire process. And I'm focusing here on secondary rays. We have primary rays investigation in our papers. Just go and read those if you are more interested. And you can see here our approach is quite competitive in that sense that it is able, at least even for Dragon, maybe you've seen the sword, they can bring down the iterations by about 58%, and we even achieve for power plant, like bring down the very expensive regions up to 80% in the CPU version, and our GPU version still manages to bring those down by 40, 30, or 50%. So how does that map now to performance? That was the most interesting question that we had. And actually, I'm proud that we can talk about gigaarrays, not megaarrays, which I've read a lot in the papers. I showed the total numbers here in the bottom, and I have the relative values here at the top graph. And as anticipated by SEH already, Whiteout and Dragon just merely benefits from it. So we just have 3 or 4% of improvement for the GPU version and 6 or 9% for the CPU version. So there's definitely caveats to it, and it really depends on what scene you're using it. However, for the scenes where you have heavily non-axis line geometry, like for power blend and bistro exterior, you see a huge benefit. So our CPU version is able to improve the performance by a factor of 2. So that's also quite significant. And still, our simpler heuristics are able to achieve an increase with 47 or 65%. So that's definitely something where we see some potential. And there's also a gap which we, in the future, are trying to close. In terms of build time evaluation for the GPU variant, that's something that I also wanted to show in this presentation. If you look at the individual phases, so that means like all the steps we need to do in the build, it's important how long our extra step takes to construct those OBBs. And we picked like from smallest team to the largest team, wanted to see how that behaves. And our goal was to stay within the budget of 20% or 50%. And this is actually something that we achieved across all the scenes, that you stay within 7 or 16%. And for the largest scene, it takes 5 milliseconds to complete, compared to the total time that you spent in your build. And that's definitely something that we thought is competitive or acceptable in that sense that you can do it. There's still other questions and caveats to it, but the simple heuristics allows us to do so. So in conclusion, what the most important things that you should take away is that we use a fixed discrete set of rotations that is predefined. We use a single OBB transform for all the children at each interior node, and we have hardware-accelerated row VB intersection. The traversal performance is something that I already mentioned in terms of where you can see the variation between like the minimum gains and maximum gains. But that definitely shows that it's scene-dependent and also depends on the effect. What we encountered is for secondary rays, we saw more benefits. So definitely there's potential of using it if you have diversion workloads and rays. And definitely caveats to it, so you need to really consider if it's worth the effort depending on what scene you have. And the build times is already something that I mentioned in the previous slide. I just listed it here. So in conclusion, also for future work, we try to close the gap to the CPU implementation. And there are definitely ways to explore it further, like for dynamic scenes, in combination with ABBs, using it with primitive splitting, do orientation-aware clustering. There's definitely potential for more work. And I wrote down the context, so if you want to contact us, Alain, I also want to thank Alain here for his work because he did a lot of effort into making this happen. So thanks for all of that. And there's also a special thanks slide for all the contributors. Thank you very much.
Thank you very much. We have time for questions.
There's one over there.
Oh, okay. Well, I was going to, before I go, I have one my own. I was curious. So you choose your parents' orientation based on the child with the biggest bounding box.
Right,
I was just wondering what happens with, say, a scene. Well, I was thinking a set of louvers. So they're all quite oriented, but they're all stacked vertically. So this one would choose. So maybe your bottom louver would choose this orientation. So would the one above, but the parent itself perhaps would be better off with a vertical orientation.
And this is
how often does that occur?
Yeah, this can occur, and this is something that you see in the gap, basically. Because if you look at the CPU implementation, you have the potential to use a better orientation. So that means a different alignment would be better. And there is where we see some gaps. For instance, with the bistro scene, I don't have it here right away. I need to scroll back. But yeah, this is something that we're trying to close. So I mean, explore like if there are different ways of using a different heuristic or maybe some additional information to choose for internal nodes what to take here, what rotation. But we basically bridged from performance versus quality, and this is something that we came up with in the GPU implementation.
Okay, so I'm not sure if that question is in the part of the previous question, but the paper is about post-processing of already existing BVH that is based with classic block or H block, but it's based on axis-aligned boxes. Was there exploration around block that in its metrics actually considers that the box could be rotated?
So you mean like already taken into account the... You mean take into account the orientation like right away from the start if you use H-block? Yeah, I mean, that's something that also my colleagues started to look into. That's definitely something we wanted also to have a look at. In this work, it's basically just the first try of seeing what's possible, but it's definitely worth exploring that algorithm and already be aware of the orientation and maybe use that information during the BVH2 build. Yeah.
Do we have any other questions?
And this sure is a very ignorant question, but you pre-select the kind of like discretization of rotation and everything, right? And this, in the end, to me seems like basically a compression attempt to compress the information. Could you have like done the opposite, like create a dictionary from the arbitrary rotations? Like
you mean like you have the scene geometry and then you, based on that, pick or define them?
You have like the arbitrary kind of rotations and then you see which ones are the more popular and stuff like that. And
in our case, what we came up with a simple representation which we can, simple set of rotations which we can control beforehand easier. So we already can pre-compute all the lookup tables. And that makes it easier for encoding, right, and also decoding, which just you limit it, right? If you have an arbitrary orientation that you would allow or some more flexibility, that also means it has more cost to decode it, right, to reconstruct it, so that involves more work. And in our case, we focused on that. We tried different approaches. We also tried like being more flexible in that sense, but that's all what it boils down is in terms of how much you want to compress, how easy it is, right, to encode, decode, and how much flexibility you want to allow. It also depends on how large your cache line is, or like how your internal nodes is actually structured.
Okay, I think that's all the time we have for questions. Obviously, we can ask questions in the break afterwards, but we'd like to thank Mikhail again